Hi again, everybody. Welcome to our second video on trigonometric substitution. In the first video, we learned that when we see something in the integram that looks like a squared minus x squared, a useful substitution might be x equals a sine of theta. In this video, we're going to consider a related expression, namely a squared plus x squared. And it turns out a good substitution in this case is to let x equal a tangent of theta. All right, let's try an example. So say I wanted to find an antiderivative for 4 plus x squared to the negative 3/2, or if you like, 1 over 4 plus x squared to the 3/2 power. So this has the right form. You have some number squared plus x squared, 4 plus x squared. So I'm going to use this substitution. So we let x equal, in this case, what's the a? Well, it's the square root of 4, which is 2, tangent of theta. Okay, now I need to know my dx, so I take a derivative. You got to remember the derivative of tangent is secant squared. So 2 secant squared theta d theta. Okay, so now I'm going to do my substitution. So let's see here. First, my dx becomes 2 secant squared theta d theta divided by, 4 plus x squared. So x was 2 tan of theta, so x squared is 4 tan squared theta. And of course we have to the 3/2 power still. Okay, now we play the same game that we did when we were making our sign substitution. I'm going to factor a 4 out of this expression so that I get 4 times 1 plus tangent squared theta. And this, we know from our other results on trig functions, is equal to secant squared. So that is secant squared theta, which is why we want to do this substitution in the first place. Once we do it, we're always going to get a squared secant squared theta. Okay, so now we can do a little bit of simplification. So I have 2 secant squared theta d theta over 4 secant squared theta. But we can't forget we have a 3/2 power. Okay, this is actually going to be really, really nice. Let's jump over here. So first, when I take the 3/2 power, the 3 part means a cube, and the half power means take a square root. Let's do the square root first. If I take the square root of 4 secant squared, I'm going to get 2 secant. Okay, so this bit will give me 2 secant of theta, and then I need to cube it. When I cube 2 secant, I'm going to get 8 secant cubed. So I get 2 secant squared theta d theta over 8 secant cubed. And now we're in a really good position. 2 over 8, that's going to give me a 1 over 4, which I can pull out. Secant squared over secant cubed, that's just going to give me 1 over secant. And then I have a d theta. Now 1 over secant sounds scary, but remember, how is the secant defined? It's the reciprocal of the cosine. So this is just the reciprocal of the reciprocal of the cosine. The reciprocal of the reciprocal, it's like you didn't do anything. It's just the cosine. So this is 1/4 integral of the cosine of theta. Hey, we know an antiderivative for cosine. It's just sine. So this is 1/4 sine of theta. Of course, plus a constant. Are we done? If only. Remember from the last video, if we end up with a theta, we're going to have to convert back. All right, so we got to go to step 2, and that's where we play with the right triangles and find our arc functions, etc. All right, so let's come back to this in a moment. All right, so we found an antiderivative. The only problem is that it's in terms of theta, not in terms of x. So, like before, we're going to solve this substitution equation for theta. When we do that, let's see, you divide x by 2 and then take the arctangent. So we know that x over 2, take the arctan, that will equal our theta. All right, fine. We can plug that in for theta now. And what are we going to end up with? A fourth sine of the arctangent of x over 2. And that's that situation we didn't really want to be in, right? Where we have a sine of an arc trig function. But we know how to handle that situation. We draw a right triangle. Okay, here's my right triangle. Okay, there's going to be my theta, and my theta is arctan of x over 2. Now, recall, the first thing I do is just write down this expression and take, well, this is arctan, so I'm going to take the tan of it. So tan of arctan of x over 2 equals x over 2. Hey, that's really nice, because I know how to find the tangent. I take the opposite over the adjacent. And when I take the opposite over the adjacent, I need to get x over 2. So I make the opposite x and the adjacent 2. Now I use the Pythagorean theorem to get the hypotenuse. So I take the square root of x squared plus 4, or I'll write it as 4 plus x squared. Okay, so now going back to our solution, I can rewrite sine of theta as sine of arctan of x over 2. And now I can use the right triangle to simplify the sine of the arctan of x over 2. There's arctan of x over 2. What is the sine of that angle? Well, the sine, let's see, that's the opposite over the hypotenuse. So the opposite is x. So x over the hypotenuse, root 4 plus x squared. All right. Okay, so once again, we've been able to use this triangle to great effect to simplify a little bit. But more importantly, the grander scheme of things, we have found another very profitable substitution that uses trigonometric functions. In the third and final video for trigonometric substitutions, we're going to see what happens when I take x squared minus a squared instead of a squared minus x squared.